Okay, so let's get started. It is my pleasure to introduce today Lauren Weiss, who is visiting us from University of Montreal, which is currently a Trotter postdoctoral fellow, moving soon to Hawaii. Which is kind of nice, I guess. So Lauren graduated from UC Berkeley, and she's done a lot of work on the exoplanet characterization using big telescopes like Keck, and doing very important work on not only characterization but also ensembles of planetary systems, so planetary statistics. And today she will tell us about exoplanet systems as laboratories for planet formation.
Thank you for the introduction, Cristobal, and thanks all for having me here in Toronto. So I actually grew up in Rochester, New York, just across the lake, so it's a pleasure to be back in the area. So, as Cristobal said, I'm doing a lot of exoplanet characterization, and the work I do is all geared toward using real exoplanetary systems as laboratories in which we can test our ideas about how planets form. So what kind of tests can we do? Well, we can ask which planets are common. It's a pretty basic question. We can also try to investigate what are the properties of the most common planets. And this is a little bit more open-ended. What are their densities, their orbits, their host star properties? Toward the middle of the talk, I'm going to switch gears a little bit and focus on the properties of multi-planet systems. These are really wonderful laboratories because in each multi-planet system, the planets all formed around the same star and really just have and formed from the same protoplanetary disk. So this is a really nice controlled environment in which we can test the physics of planet formation. And finally, I'll chat a little bit about the future. Okay, so which planets are common? As we all know, the Kepler mission was designed to do exoplanet statistics. It stared at 150,000 stars without blinking for 4 years in order to count which planets are the most common. And here is the latest plot showing the Kepler Hall. This is from the DR25 release in June last year. So this is just showing planet size versus orbital period. And as you all know, Kepler found a lot of planets that are smaller than Neptune and with orbital periods closer in than Mercury. Mercury orbits at 88 days. So most of these planets are small, close-in planets, of which we have no analog in the solar system. So how common are these planets exactly? By counting up both the transiting planets and planets that either transit but weren't detected due to sensitivity or that don't transit due to geometry, we can determine that about half of Sun-like stars have at least one Earth-sized or larger planet within 100 days. Similarly, small planets can be counted up and are quite common. So from Pettigura et al., we learned that 1 in 5 Sun-like stars has an Earth-sized planet in the habitable zone. And again, there are just many, many planets that are smaller than Neptune. And this commonality of planets was originally studied for FGK stars, but also extends to M-dwarf stars, where small planets might be even more common. Okay, so what are the properties of these common planets? Well, to really understand these planets, we need to use multiple types of observations. Kepler observed transits of planets, and from transits we get a very precise measurement of the orbital period of the planet, the time of transit, and we get the planet radius to some precision. We can also maybe measure the inclination of the planet, mostly from the fact that it's transiting. But we miss out on some other properties that we'd like to know. With radial velocities, we can fill in some of those properties. By getting just one high-resolution spectrum of the star, we can determine the stellar properties, including the stellar radius and mass, which then help us refine our understanding of the planet radius and do a better characterization of the system as a whole. We can also measure the eccentricity of the planet, and we can measure the planet mass through the m sin I measurement. But since the planet is transiting, we can combine the known inclination of the system with the m sin I to get an absolute mass of the planet. With radial velocities, we can also sense non-transiting planets and add knowledge about the whole architecture of the system. So I've used transits and RVs in combination for a lot of my work, but I'm mostly going to talk about some population overview stuff today, including how I use these two methods to answer a question about the compositions of the sub-Neptune-sized planets. So in our own solar system, we have Earth, a terrestrial planet, Neptune, an ice giant. And then, of course, most of the Kepler planets are of sizes between Earth and Neptune. And we have no such representative in the solar system. So are these intermediate-sized planets rocky like the Earth? Are they ice giants or gaseous like Neptune, or are they something else? Well, to understand this, we need to measure both the radius and mass of a sub-Neptune-sized planet to calculate its bulk density. So in a project that I led back in 2014 with my thesis advisor, we found that the densities of small exoplanets reveal a transition in planet composition. What I'm showing here is planet density on the y-axis and planet radius on the x-axis. And so far, the only data I'm showing are blue diamonds from solar system planets. We have the terrestrial planets here. They're small with high densities. The ice giants are larger with low densities. And of course, we don't know what to expect for these intermediate-sized planets that Kepler found. Here are their densities. The gray circles are masses that come from radial velocity measurements, and the gold circles are masses that come from transit timing variations. The size of the circle corresponds to the statistical significance of the measurement, where larger points correspond to more secure density measurements. You can probably, by eye, already see a pattern emerging. So let me fill this out for you. The blue squares now are showing the weighted mean density in bins of half an Earth radius. So you can see by eye that the planet density increases with increasing radius up to about 1.5 Earth radii, and then abruptly the density decreases again with increasing planet radius. This peak at 1.5 Earth radii was identified for the first time in this work. And we interpret this as a transition in planet composition. The only way to make planets that are larger than 1.5 Earth radii decrease in density is by increasing the volatile fraction in these planets. So we interpret this decreasing density with increasing planet radius as due to the admixture of volatiles. Well, what about the other side of this plot? Why does planet density change with radius for smaller planets? Well, we interpret this as the compression of rock, where planets that are smaller than 1.5 times Earth radii are very likely rocky. Of course, if you take a rock from the garden and try to crush it in your hand, you won't be very successful because rock is not particularly compressible. But at high pressures that correspond to planet interiors, rock is actually slightly compressible. And you can see that Mars, Venus, and Earth all happen to lie on a line. And they have, of course, terrestrial compositions with about 30% of their interior in an iron-rich core, and the other 70% or so in a silicate-rich mantle. And it just so happens that the exoplanets we have found at 1.5 Earth radii fall on this exact same line as our own terrestrial planetary systems. So this represents a transition in planet composition where planets smaller than 1.5 Earth radii are mostly rocky, and planets larger than 1.5 Earth radii are almost never rocky. Okay.
I wanted to ask, you've got a bunch of points way high up in density.
Yeah.
Are those large error bars? Or?
Yeah, those are large error bars because they're small points. So they're consistent with having rocky compositions. They don't have to be uranium or something weird like that. So, of course, for these 65 planets that we've just discussed, because we have mass measurements and also high-resolution spectral follow-up, we had very precise radii for all of these planets. But for most of the 4,000 or so planets that Kepler characterized, the planet radii were originally very uncertain. The typical uncertainty in the stellar radii of the planet host stars is 40%, which can correspond to a factor of a few difference in planet density. So when we look at the fraction of planets as a function of planet size, any features in this plot are distorted by the fact that we don't know which bin individual planets should belong to. So enter the California Kepler survey. This is my team and me in Hawaii. It was really nice there, which inspired me to go be there for a while. And what we did for 3 years is we used Keck high-res to obtain high-resolution spectra of the stars that host Kepler planets. So we studied over 1,000 planet-hosting stars with over 2,000 planets to get more precise stellar radii, which then turn into more precise planet radii so that we can understand the radius distribution of planets. Plus, for free, we get all sorts of wonderful properties about their host stars. Here are what our spectra look like for a variety of different temperatures. So this is the magnesium B triplet, and you can see how it evolves with stellar temperature. With these high-resolution spectra, it's very easy to assign the correct temperature, surface gravity, and rotation to a star, and with the use of model isochrones to fit a mass and radius. So with these new high-resolution spectra, we suddenly went from radius uncertainties in the star of 40% to 10%. And those radius uncertainties propagated to the planets as well.
What accuracy do you have in rotation?
And V sin I, 1 kilometer per second for any stars with V sin I larger than 2 kilometers per second.
So you can get some reasonable, what are they called, chronological dating?
Not necessarily. So most of these stars are actually pretty old, like more than 1 billion years old. So gyrochronology doesn't really work for them. Yeah, but that's actually with Gaia now as well. And the K2 mission studying lots of younger stars. That's an area that I'm really interested in understanding more about. So we should chat later.
So how precise was your metallicity?
The radial velocity?
Yeah,
What?
The metallicity.
The metallicity, 0.04 dex. So with these improved stellar radii, we get improved planet radii. So now when we count up the number of planets as a function of planet size, we identify that there's a gap in the distribution of planet radii, where planets that are about 1.3 Earth radii are fairly common. Planets of 1.8 Earth radii are less common, and then planets of a bit more than 2 Earth radii are once again fairly common. We attribute this valley in planet radius as evidence that there are 2 distinct populations of planet sizes. There's a population of rocky super-Earths and a separate population of volatile-rich sub-Neptunes. And indeed, this gap in planet radius corresponds to the same size as the peak in the density versus radius distribution. So we now have a fairly consistent story describing the sizes and compositions of small planets. However, we're not quite certain yet what physics corresponds to the creation of this gap. It's possible that some sort of atmospheric mass loss mechanism removes the envelopes of 2 Earth radius planets and leaves behind barren rocky cores. But this is still very much an active area of research.
So, trying to do a sum over this thing, it still looks like there's more 2.5 radii bodies than 1.3. Is that actually true or not?
I mean, that's hard to know because Kepler is less sensitive to 1 Earth radius planets than 2 Earth radius planets, so I wouldn't bet my money on it one way or the other. Okay, so this is all exciting physics. But now I want to turn back to multiplanet systems. Systems where, as I said, the star and protoplanetary disk are the same for all the planets. So by comparing the properties of one planet to its neighbors, we can really test the physics of how planets are forming. So I will introduce here two papers, CKS 5 and 6, which are my attempts to use the California Kepler survey on the Kepler multiplanet systems. So with these new precise stellar properties and planet properties, what new things did we learn about the Kepler multis? The California Kepler survey yielded precise parameters for 909 transiting planets in 355 multiplanet systems. And here I'm just showing the systems with 4 or more transiting planets. This plot is showing each row corresponds to one individual planetary system with the star on the left. The x-axis is AU in logarithmic units. And the planet sizes are scaled. So the smallest points are about 1 Earth radius, and the larger points are about 10 Earth radii. Also, the colors correspond to the equilibrium temperatures of the planets. So I appreciate that it's really hard to see what's going on at the resolution of this projector. So we're going to zoom in a little bit. And I just made this plot for fun one day and happened to notice something. So I'm going to quiz you and see if you notice any patterns.
Radii are very similar.
Yeah. Awesome, that's like the fastest anyone got it. So planets that orbit the same star tend to have very similar sizes. So I've highlighted a few examples in pink boxes. For instance, for this system, you can see all the planets have similar sizes. Likewise, for this system, all the planets have similar sizes. So is this a real astrophysical feature? Well, we'll find out. But anyway, this particular sort of architecture reminds me of another system in nature. Now that it's summertime, they're fairly common. Oh, come on. Oh, please don't die. Yes. Peas in a pod. So summertime, I like peas. Does everyone like peas? Okay. Right. So the peas are all very similar sizes within the same pod, just like these planets. So we call it the peas in a pod paper, because that's less of a tongue twister than this sentence. So how do we quantify this pattern? Can we actually quantify that, that planets tend to be the same size in the same system? So remember, these are just systems with 4 or more transiting planets. But what I did is I used all of these CKS multis. So this is 909 planets with over 500 unique planet pairs. And in each planet pair, I compared the size of the outer planet in that pair to the inner planet in that pair. Oh, and I guess I should clarify, these are adjacent pairs. So transiting planets and their nearest neighbors. So you can see there's a very strong correlation between the size of a planet and its neighbor. In other words, if you find a transiting planet and you want to make a prediction about the size of another transiting planet that you haven't detected yet, you should guess it's going to be the same size as the one you just found. Okay, but is it possible that this structure, which spans from half an Earth radius up to Jupiter-sized planets, is it possible that somehow this structure is the result of observational biases rather than astrophysics? Right? We know that Kepler is more sensitive to large planets than small planets. So is it possible that we've somehow fooled ourselves? To test a null hypothesis, I designed a Bootstrap trial. So for each observed system, I used the same stellar property and the same stellar properties. So stellar radius, CVPP, which is the noise properties of the star, stellar effective temperature, et cetera, same star. And then the same orbital periods of the planets, but I drew the sizes of each planet at random with replacement such that each planet has no information about the size of its neighbor. So this is really a test of the null hypothesis, which is that planet sizes don't care about the sizes of their neighbors. And finally, I discarded any planets that would not have been detected based on the stellar properties and the planet size and orbital period. So I did this bootstrap algorithm for every single star. And
When you say you're doing random, what was the distribution?
I tried 3 different distributions. The observed distribution of planet size is a log normal distribution, and uniform. Uniform is actually a little bit silly. That's like saying there are as many Jupiters as small planets, which we already know isn't true. Anyway, they all gave about the same answer. So the answer is, this is basically what all of the Bootstrap trials look like. There's no correlation between the sizes of neighbors. So again, this is not at all a good reproduction of the observed pattern, which again is here. Come on. Oh. Here, there we go. Right, so if we flip back and forth, this might be dangerous. I don't know if I'm just out of range. I'll try going over here. OK, right, if we go back and forth, we can see that this is a much stronger correlation. And I repeated this bootstrap test 1,000 times. And in none of the 1,000 bootstrap trials did I come close to reproducing the observed correlation. OK, well, what other patterns can we find here? So I also see that it looks like planets in the same system have a fairly regular spacing. If I look at this system, at just the first 2 planets, that's a pretty good, the distance here is a pretty good prediction of the distance between the next pair of planets and that next distance. Likewise, for this system, this distance, and that distance are all pretty similar. Of course, the x-axis here is a logarithmic scale. So equal distances in logarithmic scale are equal ratios linearly. So this corresponds to equal period ratios. So what I'm using to quantify this pattern is for each triplet of adjacent planets, I'm plotting the period ratio of the outer pair of planets in that triplet versus the inner period ratio in that triplet, and iterating through all the triplets in each system. So you can only have a triplet if there are 3 or more planets. So there aren't quite as many points here as in the previous plot. But again, you can see there's a pretty strong correlation here. Again, I went through a bootstrap exercise. Here's one example bootstrap trial with no noticeable correlation. And in 1,000 trials, I never reproduced the observed correlation. So a final natural follow-up question is whether there's some connection between the planet size and spacing. So with these slightly larger planets, here it looks like the spacing between the planets is a bit larger. And with the smaller planets, the spacing is a little bit less. So the way I quantified this pattern is I plotted the size, the average size of the planets in each pair versus the orbital period ratio of the pair. And you can see there's some structure here where planets that are smaller than an Earth radius tend to have really close orbital period ratios, and the larger planets have more of a variety of period ratios. Now, I did my homework and made sure that if we placed these exact same planets at larger period ratios, we could have detected them, and that's true. So it's not that we're just missing planets here. Rather, there's some real astrophysical structure. So are there any guesses about what could be behind this structure?
Stability, presumably.
What's that?
Stability.
Stability. Yeah, so maybe hill stability, right? Yeah, that seems pretty reasonable.
How would I actually argue there's no structure? If you cut away the small planet, it's flat.
Yeah, that's right. But the small planets are important too.
So it's not exactly stability.
All right, so let's see if Hill stability works out. So it turns out that all the planets that are smaller than an Earth radius are more than 20 mutual Hill radii apart. So we know that we can actually dynamically pack planets much closer than 20 mutual Hill radii. So Hill stability is not what's driving the positions of these planets, at least. On the other hand, for the close-in planets between 1 and 4 Earth radii, they tend to be more like 10 or more mutual Hill radii apart. So this particular structure is not tracing Hill stability. So it was kind of a trick question because I don't know where that structure comes from. I hope someone will tell me the answer someday because it's interesting. But for now, it's an open question, but not Hill stability.
If you were to do some kind of cuts here, removing, say, the smaller planets, or maybe trying to break this into two sets, is there one set where you see a correlation and one where there's no correlation? Because it really does seem at the larger periods that you're not really correlated anymore.
Right. Well, at larger period ratios, yeah. Yeah, well, obviously, if you've got a period ratio of like 8, that's not related to stability. Maybe these ones are survivors of violent interactions. That's pretty exciting. Cristobal and I had like a really nice chat about that this morning. So maybe these would be really fun to follow up to see, are these more eccentric than these planets? Because they could be, but they don't have to be.
There's also selection kind of the small planet. They have to be closer than 10 days for you to find them. Otherwise, they're too hard to detect. So as a result, they also closer in and smaller spacing. But if you cut away those smaller, less than 1, I would claim it's all flat.
Oh, but I mean, I don't know. I think there's maybe still some structure here. I mean, I don't think it's as significant if you cut away all the planets smaller than 1 Earth radius. But as I mentioned, if you took these exact same planets around these same stars, but redistributed them so that they had orbital period ratios of like up to 4 or 8, we still would have been able to detect them. So, but we didn't find any planets here. So why not?
I'm sorry, is there an explanation for even just why are the sizes correlated? If we go to period.
Oh, just why are the sizes correlated?
Yes.
Oh yeah, I don't know. I know some reasons why they're not correlated. It's not stellar mass.
Can it be that the isolation mass for individual systems are really comparable on this small scale?
Yeah, I think it has something to do with the disk. That's.
Go back to the previous. You see there's an obvious progression of planet sizes towards large, long period with bigger planets. And that's naively that's the full operational issue. Larger distance, you can maintain the envelope to be bigger. So then because of that progression, you just take neighboring planets and you ask, if I plot the size of one versus the other, you naturally going to get a correlation.
Yeah, except that's not what we're actually seeing here. I mean, it's true that actually, like in 63% of pairs, the outer planet is larger, but that's not a lot when you think that 50% means that there's no pattern, right? So it's not like an overwhelming pattern. And just looking at these, right, this planet is not profoundly larger than that planet. Remember, these dots are all scaled to the sizes of the planets. And likewise, right, this planet is not profoundly larger than this planet. So while it's true that photoevaporation and envelope retention relate to how planets that are further out can hold on to more of an envelope, that's not the only pattern that's driving this nearest neighbor correlation.
It does look to me like the innermost planet in a number of cases is a little bit smaller.
Yeah, that's right.
The next innermost planet.
Yeah, I think that's
However,
true.
I mean, one doesn't have to think very long to think of many possible, like the protoplanet disk, in the innermost part is where the silicons are sublimated. you would have a very different gas surface density, probably much lower gas surface density. I mean, you know, it's not like the photoevaporation model is crazy by any stretch of the imagination, but
there's too much physics. I couldn't agree more, and that's why I love multi-planet systems, because we can test things like the dust sublimation radius and photoevaporation and all of these different physical processes that can strip envelopes and actually look at individual systems. Like even this one that's not peas in a pod, that has a large one and a small one and a large one and a small one. What's going on here? How did that happen? I don't know. I'd love to go measure the masses of these planets and then say something hopefully interesting about why they have these sizes. And if I could measure their eccentricities too, something about whether their eccentricities are higher than what we typically expect for a system that's this compact.
This hasn't been because the stars are too dim.
Yeah, they're typically 13th magnitude or 14th magnitude, even 15th magnitude.
So even with that, you can't get enough time to do this stuff
to get radial velocities, to get like many spectra. But I'll present a dream plan at the end of my talk where I will get around all of those problems before I die.
Just one moment. So I'm going to not defend the photoevaporation model because I think it doesn't need defending. But I do want to comment that if you want to show that the size correlation, inner and outer, you want to make sure you get rid of this hidden variable, which is optical separation. Because we know there's a clear correlation of size with optical separation. So you want to show that inner and outer planet correlation is something different, not just that single hidden variable, which is obvious. That takes more work.
Should there be also correlation with the effective temperature? Because you do have effective temperatures for these, right?
Yeah, that's right. So I did look at that actually, and there is a slight correlation between, how did I frame this in the paper? So I looked at the difference in effective temperature of the planets and looked at the ratio of planet sizes, I think, as a function of difference in effective temperature. And there's a very slight positive correlation, but it's not nearly as exciting or profound as like the one-to-one planet size ratios.
You must have done the exercise of showing as a function of orbital radius which of the two peaks these planets sit in.
Oh, so I'm actually kind of working on that right now with James Owen and Hilke Schlichting. So.
Well, no, I understand what you're asking. The inner one is closer in, the bigger one is further out. It's already known 5 years ago.
No, look. So sometimes they're all smaller.
No, there's two peaks in the size distribution. There are two bumps.
Yeah. So sometimes all the planets are in the small bump. Sometimes all the planets are in the big bump. Sometimes some of the planets are in the small bump. Let's see if I can find one. I don't see one here. I guess maybe this is the best example, right? This innermost planet is the smallest, and the other ones are a little bit bigger, which is of course consistent, again, with photoevaporation. And then sometimes we get these disordered multis that go big, small, whatever, or even this one, even though the closest in one is little, this one's big, and then that one's little again. So actually disentangling how to think about these systems in terms of the photoevaporation gap is not trivial. So that's something I'm working on right now and trying to figure out which of these systems are the most surprising and most in need of further observations. And I really hope more people will join in this effort. If you're a student and want to work on a project, I've published tables that have all of the planet radii and radius ratios with their nearest neighbor, et cetera. So that's available for download for you to play with.
Sure.
Yeah.
For the ones that sort of alternate inside.
Yeah.
They're both like occupying the peaks, or is like one peak and one trough? Sort of like it's actually like significantly like 2.5 Earth radii, 1.5, 2.5. So very definitively
occupying both peaks. And I think there are like 7 such planetary systems where we already have masses in Marcy et al. 2014, and more where we don't have masses, a lot more where we don't have masses. Okay, let's see, I'm gonna move on because I wanna talk to you about some other stuff. Okay, so I guess just to conclude this section, so there are 3 patterns that I would love people who do population synthesis to reproduce. One is that planets in the same system have similar sizes. The second is that they also have similar orbital, regular orbital spacing. And the third pattern is that across all systems, there seems to be some underlying relationship between the orbital period ratio and planet sizes. Okay, so now I'm going to present for basically the first time some work that I just submitted a couple weeks ago. It's not on the archive yet, but if you'd like a preprint, please ask me. So this is CKS6, a comparison of the Kepler multis versus singles. So to clarify my language here, by multi, I mean a system that has multiple detected transiting planets. And by a single, I mean a system with only one detected transiting planet, although other planets might exist, either at different inclinations or that were too small to be detected. So other people have compared singles and multis in the past. What advantage does this study bring to the table? So a particular strength is that I had spent a lot of time constructing a homogeneous sample of singles versus multis. And because it's using the full CKS survey, it's also a very large sample. So this is just an HR diagram that illustrates to some degree how I created this sample. So the CKS sample was originally a very, not at all a homogeneous survey. This was sort of constructed by multiple people over the years. And the idea at first was, let's get a spectrum of every Kepler host star brighter than 14.2. And then we said, ooh, let's make sure we get a spectrum of all the multis. And ooh, let's make sure we get a spectrum of all the ultra short period planet host stars. And ooh, let's make sure we get a spectrum of all of the host stars that have a planet in the habitable zone. So it wasn't originally a very homogeneous survey. So if you don't make intelligent cuts about which stars to count versus not count, you will get singles and multis in certain parts of parameter space that don't necessarily match up. So what I did is very carefully selected the CKS stars for which there are no false positives, no dilution from secondary sources, so no binary stars. And then I had to make a magnitude cut at 14.2 because that was the magnitude for which any star brighter than 14.2, we got a spectrum whether or not it was a single or a multi, and regardless of the properties of the planet or the star. So the final sample of singles versus multis for comparison are shown in blue and red dots, although we actually had data for about twice as many planet hosting stars. I will also briefly mention the CKS multis as a whole, which is just any multi-planet system for which we got a spectrum, and I'll compare systems that have 2 versus 3 versus 4 or more transiting planets. And so you'll see what that does later on. Okay, so the questions that I was trying to answer in this paper are which properties correlate with the number of transiting planets? Do the host star properties or planet properties in some way relate to planet multiplicity? So the answer for stars is no. The host stars of the Kepler singles and multis have indistinguishable masses, metallicities, and V sin i's. So these are histograms, just of number of stars versus stellar mass, metallicity, and V sin I. And then the cumulative distribution functions on the right, if you prefer those, with Anderson-Darling p-values showing that there's no way to statistically distinguish these distributions.
Kepler singles.
Kepler singles. Yeah, this is all Kepler singles. Oh, and one thing I forgot to mention is, since I just submitted this paper a couple weeks ago, I was able to fold in the Gaia parameters. So now the stellar radii and masses are good to 3%. The metallicities are good to like, I think 0.03 dex now. VSiNi is the same. Yeah, but we have amazing stellar parameters now. And the planet radius uncertainties are now 5%. 3% comes from, the 3% is from the stellar radius uncertainty, but then the additional part of the error budget is actually from the uncertainty in the depth of transit from the Kepler light curve, which is really amazing because these are like the most clean and beautiful transit depths we've ever measured. So it's amazing they're actually contributing to the error budget. Okay, so if you look at a host star, any star in the sky, and want to know, is it going to have one or multiple transiting planets? The host star properties are not going to tell you if it's a single or a multi. Okay, so what about the planet properties? Now here it gets a little bit more interesting. So this plot is showing planet radius versus orbital period, pretty standard, for the singles versus the multis. So the singles are red and the multis are blue. And by eye, you can probably pick out a few interesting features in this plot. So what I did is I wanted to get quantitative. So in each grid cell, I computed the fraction of detected planets that were singles, which is that number F, and used binomial statistics to compute the uncertainties. And that just helps us justify picking out a few different regions. So they're the hot Jupiters, they're all singles. That's not a surprise, I hope. There's also the hot Earths, which have a higher fraction of singles. There's a 2 sigma-ish population of cold Jupiters. A lot of these are just planet candidates that still need to be validated. So that's an exciting project for the future. But most of these planets, the majority of planets, are sub-Neptunes. And for this vast region of parameter space, the fraction of singles is pretty consistent. So let's look more at these sub-Neptunes beyond 3 days. What is their radius distribution? Well, when we plot the radius distribution of these planets, the valley is present in both the singles and multis. So again, here are just the number of planets versus radius for the singles in red and the multis in blue. And you can see quite clearly the gap in both of those distributions. There's a CDF on the right, if you prefer that version. And then I mentioned earlier that I would use the full sample of CKS multis for comparing different transiting multiplicities. So here you can see systems with 2, 3, and 4 transiting planets, and then the cumulative, the sum of all of them in black. And there's this very clear gap in planet radius for the multis. So if you weren't really sure if the gap was real or what, I think it's pretty real. And it's interesting that whether a planet is a single or a multi, it respects the physics of this planet radius gap. Okay, finally, let's look at planet orbital periods. So among the sub-Neptunes, there are more short period singles than multis. So here's just the histogram of orbital period, and you can see there's this population of ultra short period planets below 1 day, and then also more singles with sort of less than 3 to 10 days. And then from 10 days on, there are about just as many singles as multis. So that's pretty interesting. And you can see in the CDF that there's this clear excess of singles over multis that's statistically significant. But when we look at just the multi-planet systems with different multiplicities, 2, 3, or 4 transiting planets, there's no excess of any particular multiplicity over any other. So What this means to me is if someone said, Lauren, I know how to explain this excess of singles, it's because if you have a planet very close to its star, it's very unlikely that the next planet out will transit. So you're going to find more singles than multis. Well, that's true, but if that's the case, I would also expect that we would see more systems with 2 transiting planets than 3 transiting planets at those same orbital periods, and likewise more systems with 3 than 4 transiting planets. But we don't see any differences in the distributions of the different multi-planet multiplicities. So what this suggests to me is that this excess of singles compared to multis is likely architectural in nature rather than due to our viewing geometry. Perhaps there are 3 different things I could think of. Perhaps these are truly singles where the actual underlying planet multiplicity is different. Perhaps these planets have a different inclination distribution, or perhaps they have a different period ratio distribution, meaning that they've somehow been, by physics, brought inward closer to their stars. And it could be some combination of those 3 different possibilities. So I don't know the exact physics of why we are detecting more singles at close orbital periods, but people like Cristobal and others are working on it.
In that part of orbital dimension space, is there any greater tendency for the planets to be the lower size peak?
Yes. Yes, that's a great question, and the answer is yes. So for planets that are, this is what Yanshin has been saying, for planets that are really close to their stars, sort of like 3 days or 10 days, they tend to be photoevaporated. Especially all of these ultra short period planets are rocky.
But you see, I mean, they also tend to be more likely to be single.
Yes.
That then raises a question mark over photoevaporation and suggests that perhaps more it's interactions that are playing a role in moving atmospheres, which of course is super easy. I mean, you think what's happening with coral Mercury, right? And that's sitting way out. And it seems to have, as I understand the leading model for its extreme metallic contact is that it underwent a big collision.
Yeah, of course, Mercury is at 88 days, so that's like,
so
yeah.
The silicates, 88 days, things can happen to a poor tenuous atmosphere close in.
Yeah.
I mean, hardly the
Right.
first person to raise this issue, but you know, but the fact that you have some additional information about the singles versus the multiples is you know, potentially a clue here, isn't it?
Yeah, I think this is a really important clue. And actually what I'd like to see the people who build models do is reproduce these distributions in your models. Yeah.
They are just short.
Yeah, yeah. So if you can make your toy model reproduce these these cumulative distribution functions, not just singles versus multis, but also make sure that the different high multiplicity multis all respect this sort of native architecture that they came from. That would be great. Yeah.
So just one comment though. So the period or the detections of the planets in the same system are correlated. So it's fine to plot the cumulative distribution of period of single transit planet system, but if you plot the period distribution of particles, then it's not exactly the underlying distribution anymore because of this correlation. And second, we've showed in our paper that these single transit planet systems, majority of them are in fact multi-planet systems with large inclinations.
That's, as I said, one possibility.
But I'll just say, if you detect one transit planet out of a multi-planet system, then the system is more likely to have, let's say, maybe 2 or 3 planets. But if you detect 2 or 3 transit planets, then the system is almost certain to have 4, 5, or 6 planets.
That could be the case. whatever you have in mind, see if you can fit the data, because as you say, these are not the underlying distributions, but whatever the underlying distribution is, you should be able to, apply, as you say, basic geometry to figure out which ones are transiting and detectable as well, and just make sure you get the same distribution back. Okay, so just to conclude this part of the talk, if you look at a particular star in the sky, you can't figure out if it's going to be a single or a multi. The planet properties themselves also are not particularly indicative, right? All of these, the multis and singles all had very similar radius distributions. So what this is telling me is that the singles and multis from Kepler have a common origin, but they tend to form in the same way, and that it's some later dynamical process that results in their orbital periods having this funny feature. Okay, I wanted to talk about like a survey that I'm running, but I totally am out of time here. But if you want to hear about my search for Jovian companions to small transiting planets.
You have a few minutes, but you
oh.
will not have questions. Sorry, there's a couple of questions. Oh, we got some people.
Okay. Well, okay, I don't know. Do you want me to talk about this or conclude? Oh, you guys go to 410?
Yes, sorry.
Right.
Oh, okay. Okay.
You'll have less time for questions.
Yeah, okay. Yeah, I'm not on Toronto time, clearly. Okay, okay, well, I'll go through this quickly. So I'm interested in what is the connection between giant planets and the planetary system interiors. So with Kepler, we found all sorts of transiting planets. But what we don't know is whether these Kepler multis have Jupiter analogs. Of course, here's our solar system, but our Kepler sensitivity was only out to maybe about 1 AU at the best. And of course, some folks here have been working with existing data to try to answer this question. The way I'm attacking it is by getting radial velocities of Kepler planetary systems. So the idea is whether Kepler found a single or a multi or whatever architecture it found with small planets, I want to know what kinds of planets are in the outer planetary system. And to pursue this, I'm getting radial velocities with Keck high-res. So our survey that I've designed will be sensitive to Saturn mass planets at 3 AU for about half of our stars. And the questions I'm addressing are, what are the masses, orbital periods, and eccentricities of the giant planets? And how do the properties of giant planets around the multis versus singles differ? Is there some way that we can understand singles versus multis in the context of giant planets? And just overall, how do these giant planets influence the formation of sub-Neptunes and terrestrial-sized planets? So we've been doing this survey since before I was a grad student, so it's a little presumptuous of me to take it over, but that's what I've done. And here's a preliminary result. So we've found a bunch of giant planets inside about 2,000 days. So this is actually already published in the literature, but we've had more data since 2014 when this is published. So this is a system that has one small transiting planet, which if you look at the curve, that's that little fuzz to the fit is from the small planet. There's also a giant planet with a period of 500 days and about 5 Jupiter masses. And then you can see there's a very obvious trend here from an even longer period planet. Here's another example of a system with, again, one small transiting planet and a really massive 10 Jupiter mass giant planet and a period of 2,000 days. This is not published yet. This is just turned over, and I'm going to continue observing this to see if there's a trend indicative of yet another companion. Some words about the future. I can really skip most of this. Oh, I can't skip this. Okay, you guys know about Tess. Tess is going to be great. It's finding planets around the nearest stars. We're going to be able to follow them up because they're brighter than the Kepler host stars. But the secret to doing all the science I want to do before I die is the Keck Planet Finder, which is scheduled for first light in 2020. This is a brand new state-of-the-art radial velocity spectrograph that is going on Keck 2. The KPF will deliver radial velocities with precisions of 0.5 meter per second. And what this will do is KPF will expand our reach to smaller planets around fainter and redder stars than we can currently observe with Keck high res. So this plot is showing the population of test planet candidates. On the y-axis is the Doppler semi-amplitude of the star moving from the planet in meters per second. And on the x-axis is stellar magnitude. With Keck high res, we're currently sensitive to this part of the plot, and we will be sensitive to a lot more planets with KPF, including many, many terrestrial-sized planets. A few of my favorite systems, some of you know I worked on Kepler 10, that's here. I did it with Keck high res. It took about 200 RVs to get the masses of these planets, and that was still really challenging. But with KPF, we'll be able to hit Kepler 11, which has 5 planets that all orbit within the orbit of Mercury, 6 within the orbit of Venus. It's a wonderful system. It already has TTV masses, but it would be nice to get precise RVs, partly to confirm those masses, but also to look for additional planets in this system. Also, we might be able to access Kepler 444, which has 5 Mars-sized planets in the system. And finally, the project that I'm really most excited about is going back to these peas in a pod systems and finding like 100 or so that sample the diversity of multi-planet systems, compact systems, systems where the planets are spread out, the disordered multis where the sizes don't seem to really relate to photoevaporation, ordered systems where we think we know what to expect. And for 100 multi-planet systems that span the diversity of multi-planet systems, just measure what are the masses and eccentricities of the planets in these systems and what other planets are out there. All right, so I'll put up my conclusions there, and thank you all for your time and your attention and your questions.
So we have time for a couple of questions. Otherwise, we continue the discussion upstairs. We have enough questions there at the top, though.
I'm thinking that's going to be solved in 2 minutes.
No.
Well, is there, you were showing similarity in the distributions of planets in kind of this spectral type.
Mm-hmm.
But is there not any correlation between the total mass of planets in these Kepler systems and metallicity? Is that really absent?
Oh, between planet. So for most of these planets, we don't have masses yet. That's why I want to get them.
So, right. So these other ones
we have looked for correlations between planet size and metallicity. Yeah. So Eric Pettigrew wrote a really nice paper about that. It's called CKS4, metallicity, radius, and occurrence, or something like that.
But you don't have enough information for some subset of systems from like kinds of timing on the masses to begin to say something about correlations
between planet mass and metallicity?
Total mass and metallicity.
Oh. Well, total mass is also hard because you don't know which planets you're missing. So that gets a little dangerous
for that reason. There are also the priors.
Yeah, but there's a very slight correlation between planet size and host star metallicity, but it's nothing to write home about really, or at least for the sub-Neptunes. For the giant planets, there's a strong correlation. Likewise with, if you go back to,
well, there are results about the occurrence of metallicity, right? There's no particular correlation there, unlike the Jupiters.
Sorry?
Yeah, that's right.
There's no correlation. Go ahead. You can
between the occurrence and metallicity. Yeah, so that was also part of CKS4 was occurrence as a function of metallicity, and I don't remember if there was any correlation, but it was not something worth writing home about. likewise, something I've actually observed but not actually formally published here is that there's not really a correlation, no strong correlation between planet size and stellar mass. Remember, these systems are ranked by stellar mass, and you can see that knowing the mass of the star doesn't help you predict the sizes of planets that you're going to make in that system. So I think there actually might be some weak correlation that's statistically significant, but again, it has very little predictive power.